Joining us today, we have Dan Dawson, Assistant Professor of Atmospheric Science in the Department of Earth, Atmospheric, and Planetary Sciences at Purdue. So welcome, Dan.
Thanks. I'm glad to be here.
Yeah.
We were very excited that you were going to have time to do this. And I know we were hoping to get you a little bit earlier, but getting you in the spring is not a time that we're going to get you. Being a storm person, and so I guess I'll have you explain that, kind of what you research, so that people will know why the spring is if you have free time, you're out chasing something.
Oh, sure. Yeah, absolutely. So my area of research is essentially the dynamics of severe thunderstorms and tornadoes. And I do a combination of, I use a combination of tools to study them. My main one that I use most of the year is computer simulations, and analyzing the output of computer simulations to understand different aspects of storm behavior and tornado behavior. But I also do quite a bit of observational data collection. So I've been involved in different field programs. I was involved back in 2009, 2010 in the VORTEX-SE field program, which was a very large multi-institution mobile program to essentially chase storms and tornadoes and study them with a whole array of instruments. The original project, VORTEX, was, by the way, VORTEX, it's an acronym. We love acronyms in atmospheric science, but it stands for Verification of the Origin of Rotation in Tornadoes Experiment. And the original was in 1994 to 95, and that was back when I was in high school, so I wasn't part of that. But VORTEX-2 was in 2009, 2010, and most recently, since I've been at Purdue, I've worked with the VORTEX Southeast field program, which is a similar program, somewhat different in that it's not, up until possibly recently, it's not really NSF sponsored, but it's a NOAA directive from the National Oceanographic and Atmospheric Administration. But the goal is to study severe thunderstorms, potentially tornadic thunderstorms in the southeast U.S., where certain signs point to there being somewhat different environments that are more frequent in the southeast U.S. That are conducive to tornadoes than the ones that we're used to in the Great Plains and even in the Midwest. And so we're studying how those environments, how they differ, how the storms that form in them differ from their Great Plains and Midwest counterparts, and how well we can, whether we can improve the predictability of those types of storms. Southeast U.S. tends to have a larger proportion of their tornadoes tend to occur at nighttime and occur from linear convective systems, instead of discrete rotating storms called supercells, which the vast majority of tornadoes form from. They also get those in the southeast, but there's a greater proportion that come from these sort of basically squall lines with circulations embedded in them. They tend to be weaker tornadoes, but they also, like I said, tend to come at night when it's hard to, when warnings are maybe not heeded because people are asleep. There's also a much higher percentage of manufactured housing, which is very vulnerable to tornado damage. And also a lot of these tornadoes tend to occur in the cool season, very early spring, maybe even over the winter time. So it's a different climate regime. So we're trying to learn how things may change, may be different down there, and what kinds of observations and techniques we need for forecasting that may not, whereas the more traditional techniques may not apply as much.
So what kind of data are you collecting? If you're researching these in different areas, what type of data is important to a scientist like yourself?
Oh yeah, so the short answer to that is anything we can get for these storms. But yeah, that's kind of flippant answer, but the longer answer is that we need data on the flow field, the flow patterns in and around the storms. Thunderstorms that produce tornadoes, or thunderstorms in general, are highly three-dimensional structures. There's updrafts, downdrafts, lots of horizontal patterns, rotation, vortices, shear. It's very complicated. And to understand it, we need to have very high resolution observations of the wind field. The only tools that we have that can really do that on the scale of the storms and over an entire storm system are Doppler radars. So we need Doppler radars at very close range. So they need, it's hard if you have a fixed site radar like the one we have it here at Purdue, the XTRRA radar, you have to wait for the storms to come by, right? And so if you wait long enough, you'll get some, and that's great, and you can learn a lot. But for this kind of work that we're doing, we need to be able to take the radar to the storms. So we put these on trucks and drive them out there and set them up and let the storms go by. We usually have strategies so that one radar is looking at the storm from one angle and another is looking at it from another angle, and their scans are synchronized so that we can get a full 2 to 3 dimensional view of the winds. We need observations of the microphysics of the storm. So by that I mean the cloud and precipitation fields in the storm. So the rain, hail, snow, and so on that are falling out of the storm. Radar can provide those observations. My particular niche has been putting these probes, instrumented probes out in the path of storm that sit on the surface. So we call those in situ. They're actually, the probes are designed to go inside the storm and measure directly inside the storm. These are surface probes, so they're kind of like smaller weather stations. Call them the portable in situ precipitation stations, or PIPS. During VORTEX Southeast, collaboration with OU and NSSL, we built 4 of these and still have them. Actually, they're sitting in my garage right now because we need it. Because of this whole COVID situation, they were going to go back to OU early in the spring, and that was right as the lockdown was happening, travel bans. So haven't been able to get them back yet, but they need to go back there for maintenance, and they use them in hurricane intercepts as well.
Oh.
Anyway, these probes have all standard weather instrumentation on them, so they have what you might expect on any regular old weather station: wind speed, direction, barometric pressure, relative humidity, temperature sensors are all on there. They also have a GPS and compass, so we can just put the probe down. We know which direction it's facing, where it is. From that, we can calculate the wind direction, and from the compass heading, and relative to north. But the centerpiece of these probes that makes them a little bit different from standard weather instruments is this thing called a disdrometer, which is a device that it's kind of a weird name, but it's essentially a device that measures raindrop sizes, or hail, or whatever happens to fall through it. Actually, it's got this beam of laser light that shines across this gap. So this beam shines across, and then there's a photodiode array on the other side that collects the light. And anytime a particle falls through that, it occludes the beam a little bit, decreases the amount of light that is detected on the other side. From that information and a few assumptions, you can tell what size the particle was and how fast it was falling through the beam. And we basically use those to count the drops as they're falling over a period of time and size them. From that, we can build up what's called a drop size distribution. As raindrops follow a certain distribution of sizes when they're falling in a storm, you got a range of the sizes. You got lots of small ones, fewer medium-sized ones, and even fewer large ones. The largest ones get up to about, at most, a little less than a centimeter in diameter. Anything bigger than that, and the air drag and turbulence associated with that will break the drops up. Surface tension isn't strong enough to hold them together beyond that size. But the reason why I'm doing this is to understand, if we understand how the size distribution of raindrops changes in these storms, we can learn something more about the physics of the clouds and the precipitation aloft that is creating these distributions. It'll tell us about the storm structure, the wind fields in an indirect way. which I can get to if you talk about that if you want. It's a little bit esoteric, but we can also calculate things like evaporation rates, because the raindrops simply fall through the air below the cloud base, which is the relative humidity is less than 100%. So the raindrops start evaporating. That cools the air off, and that creates cooler outflow and downdrafts that spread out from underneath the storm. If you have all else being equal, rain that is spread out water that's spread out among a bunch of small drops relative to the same amount of water that's tied up in just a fewer larger drops, the batch of drops that are smaller will evaporate more quickly and cool off air faster, and that can have implications for the strength of that cold outflow in the storm. And tornadoes happen to not like that cold outflow. They tend to form in storms, all else being equal, that have warmer downdrafts, warmer outflow. So this is a long way of saying that the raindrop size distributions that we see can actually potentially affect tornado development in these storms, something that you may not have expected to think. But we find these kind of connections in science a lot. And so that's one connection I'm trying to learn about. Wow. So those are the kinds of data that I like to collect. Different researchers will have different tools and instruments that they'll bring to bear on these storms to learn about other aspects of them as well. So, like lightning detection, and it's basically whenever you want to study these types of storms, you have to have a huge collaborative enterprise. No one group or team can do it by themselves. It's a very coordinated effort. And when it is all working, it's a sight to behold when you're all out there communicating in real time with all these storms around and stuff. It's kind of amazing that we can do as well as we do.
With networks of weather stations going up kind of everywhere, it seems like a lot of businesses and I know a lot of farms here in the Midwest have weather stations, and they're tied into like networks. Mm-hmm. Do you, as a scientist, do you utilize some of that data also sometimes in what you're doing?
I personally have not used like networks of personal weather stations for most of my stuff. Those are available, and quality controlled versions of those data sets are, as far as I know, are used in operations and also by lots of researchers. So yeah, it is used by the meteorological community in general. I haven't personally used that data for my own research, but it's something that I might in the future. I don't know.
Okay, that's fair enough. The next question is now. So when a front comes through, and it's really the temperature drops super fast. Mm-hmm. And so is that because of what you're saying there a while ago? Because the evaporation that's happening of the water, is that primarily why the temperature drops so fast when the front comes through?
Yeah, that's a good question. So it depends on what kind of front you're talking about. So if it's a run-of-the-mill cold front, like the kind that you see on weather maps on like TV, those are what we call synoptic scale fronts. And so synoptic scale just simply means on the scale of size of a state to the size of the country. So weather features on those scales include fronts, at least along the long dimension of the front. And low pressure and high pressure systems, hurricanes, things like that are synoptic scale. So a synoptic scale cold front, like what you're asking about, is basically marks the boundary between air masses of different origins most of the time. So, I mean, I'm simplifying things a little bit, but the idea is like you get a cold front from the north. You're getting air that has been come from closer to the North Pole, from Canada or whatever. So the air is there just colder, and it's moving into warmer air. So that is not generally from rain evaporation, evaporative cooling. But on the other end of that scale, if you're talking about what's called a gust front coming out of a thunderstorm, that air that the temperature will drop behind that kind of front, it represents the leading edge of the cold air outflow, the cold pool, we call it, of cool air underneath the storm that is on a very local scale, tends to be. And that is generated by the storm. That cold air is generated by evaporation of raindrops, also melting of hailstones. So yes, in that sense, in that situation, that would be the reason why the air temperature drops. So it just depends on what, just a regular synoptic scale cold front, and no, but certainly if you have rain falling in it, that can help cool it off. But the basic reason is not that, but for thunderstorm-induced cold outflow, it is.
And so that would be something like when our weather pattern, like it's been here every day, it's highs in the 90s, lows in the 70s, and every day, and that's not changing for a while. So if there is a big thunderstorm that comes through and then it does feel a little cooler, that's like that second thing you talked about. Is that correct?
Exactly. That's exactly right. So you probably noticed this over the last several days where we've had storms develop nearby. Even if the storm doesn't, even if you don't get any rain, like at my house, we haven't gotten hardly any rain from these, just gotten unlucky until last night when we got some around 30 in the morning. But even when you don't get any rain, you'll get those what we call outflow boundaries. The cool air will come out of the storm. It will sink in the downdraft from the storm. When it hits the ground, it can't pile its way through the ground, so it spreads out. Mm-hmm. If you don't have much wind shear in the environment, then that air will just spread out in all directions, okay, and will undercut the storm itself, and so actually will kill off the storm, because then the storm, it's choking off its warm, moist air supply. But then that cool air will blast away, and you can get, if it passes you by, you'll feel the temperature drop, the wind change direction, and the wind speed pick up for a minute. Even if you're not going to get any rain from it, you'll get that cooler air that has been previously cooled off by the rain, evaporation, and so on. So yeah, that's right.
Oh, that's pretty cool. Now, explain fronts. We haven't had anybody really explain fronts yet. I mean, I know a common question is if it's a warm front and a cold front, isn't there warm and cold on both sides? And how do you decide if it's called a warm or cold?
Yeah, so that's a good question. Right. So a front, and getting back to what I was saying earlier, in a general case, depending on, no matter what the scale is a boundary between air masses of different characteristics. And typically we're talking about temperature characteristics, but also could be moisture and so on. So the boundary between, on the large scale, boundary between different air masses that have different origins. So like a lot of times you'll get a cold front that will come, like I said, from the Arctic or the Pacific with cooler air that moves into a region of warmer, moister air that maybe has its origin from the tropical regions. So you have these air masses that sometimes are labeled different things like maritime tropical, continental, which tends to be like warm, moist air from the tropical oceans. And you have continental tropical, which is like dry desert air. And then you have continental polar, which tends to be, cool air from like the north over lands. Maritime polar be like from the cool oceans and so on. Okay. And then Arctic sometimes is put in there as a separate one. But anyway, those fronts, yeah, they're just boundaries between those air masses on that scale, on the synoptic scale. And so whether you call it a cold front or a warm front is simply which air mass is advancing for. So if the cold air is advancing, then it's a cold front. The warm air is advancing, it's a warm front. If neither are, it's a stationary front. And on the small scale, the gust fronts I was telling you about, the outflow boundaries, we don't typically call those cold or warm fronts. The dynamics of the structure of those tend to be somewhat different. They tend to act more like what we call density currents on that scale, which if you've probably seen these, if you just Google density current and look at YouTube videos, you can see, like sometimes you'll see these as like turbulent, muddy flows inside of a water tank with like lots of turbulence as the dense water with dirt and soil and stuff blasts through clear water. It's just like that, except we're talking about cold air that's undercutting and cutting through warmer air. On a small scale, that tends to be the behavior of those. So we don't really call them cold fronts, even though, I mean, you could, because they are regions where you have cooler air advancing into warmer air. Yeah.
Are there any like combination of fronts that would really be ideal for what you would want to go out and study? So is there any like if you know you're getting a front from, like you were naming the different kinds of fronts, you said I forget the ones, maritime and continental.
Yeah, air masses that are a
Oh
boundary.
yeah, the air masses, sorry. Is there any combination of air masses that would really be ideal for making a supercell that would produce tornadoes?
Yeah. So that's a good question. The very simplified answer is yes. It's a lot more complicated than sometimes you'll see people talk about, oh, tornadoes forming from clashing of cold and warm air masses. And that's one of those cases that Einstein talked about as being so simple. Everything should be made as simple as possible, right? But not simpler. And that's a case of where it's too simple. Because if tornadoes and storms like that just formed from clashing of cold and warm air masses, they would happen all the time, everywhere, because that's always happening somewhere. But what the type of environment, let me just answer that question a little bit differently. The type of environment that is conducive for tornado development and tornadic storm development tends to be an environment where you have a lot of warm, moist air in the low levels, the maritime tropical I was talking about, coming from sometimes the source from the Gulf of Mexico. Especially if we're talking about, if we just focus our energies on this discussion on the United States, east of the Rocky Mountains. That happens to be the region with the highest frequency of tornadoes anywhere in the world. So you tend to have in the low levels the maritime tropical air mass with air moving from southeast to northwest. Okay, so low level southeasterlies. We're talking about in the lowest couple kilometers of the atmosphere. Above that, you tend to have drier, hot air that's coming off of the deserts in the southwest. Those are from the southwest. So you have southwesterly dry, warm air, continental tropical air that moves over the top of this warm, moist air coming from the Gulf, because the terrain up to the west is higher. So as it blows over or moves east, it blows over the top of the warm, moist air. And then above that, you tend to have your strong jet stream westerlies, cool air way high up in the atmosphere, 6 kilometers and up. And so what you get two things. You get two main ingredients here. You get in the temperature, what we call the thermodynamic profile, the temperature profile, you have a decrease in temperature with height, fairly rapid. And you have a lot of moisture in the low levels, trapped in low levels. Moisture is the fuel to produce the storm clouds. As that moisture rises, the air cools off, reaches its dew point, the water vapor in the air condenses into clouds. Condensation is a heating process. Okay, it heats up the air. That gives the air more, makes it more buoyant, makes it less dense than its surroundings that it's going through that's dry. And so it will, when it becomes less buoyant, or more buoyant, less dense, it will rise faster, it will accelerate upward. That's the energy that generates the accelerating updrafts of these storms, comes from that moisture, okay, and the warmer air in the low levels. So that's the thermodynamic setup. You need that piece, that's one ingredient, okay, that will power your storm updrafts, okay. Every storm, thunderstorm that you see, cumulonimbus, is buoyantly driven in that way, where the warm, moist air near the ground is accelerating upward in the updraft. That's not enough for a tornado, as if it were, every thunderstorm would be producing tornadoes all the time. They don't. Most of them don't. The vast majority of thunderstorms don't produce tornadoes. So something else has to be going on. And in fact, the key to a type of thunderstorm that will be more likely to produce a tornado is the wind profile and how that wind profile behaves. We're talking about the wind profile in the atmosphere, the large scale atmosphere. So we're talking about, as you go up, you get these horizontal winds from all different directions on a large scale. The storm itself will have a wind structure that will be very complex. I'm talking about before even a storm develops, what does the wind profile look like? That's very important. So I mentioned the southeasterlies and the low levels. So you tend to get the type of environment that favors tornadic storms in this part of the world tends to be southeasterly winds in the low levels, turning to the southwest and then west as you go up, and increasing in speed that whole time. And that was what we call vertical shear of the horizontal wind. The wind is changing direction, and it's also increasing in speed with height. So that's wind shear. And if you think about if you were to have some giant paddle wheel stuck in the atmosphere on a horizontal axis, okay, and you set it up such that the winds 6 kilometers up were blowing across the top of the paddle wheel, the winds down near the surface were blowing along the bottom, you could envision this as causing the paddle wheel to start to rotate because the winds above are stronger, so they're going to be pushing on the top harder than on the bottom. So the whole thing will start to rotate around a horizontal axis. So shear has this sense of what we call vorticity, which is a local measure of the rotation of the fluid. Doesn't mean that the fluid is actually rotating like a vortex. It means that there's that potential for rotation. It's a local measure of rotation. So that horizontal rotation when you have enough of that wind shear and you have a storm developing in that type of environment, the updraft will form because of that buoyant accelerating air. It will rise up from the low levels and push through the air mass above it. So it will encounter stronger winds from different directions as that updraft rises. Okay, with me so far?
Mm-hmm.
Yeah,
okay.
yeah.
So because that updraft is encountering different winds from different directions as it moves upward, it will actually start to interact with that horizontal rotation and tilt it upward from a horizontal axis to a vertical. And it will intensify and stretch it out, just like if the proverbial figure skater on ice, pulling their arms in, spinning faster. That shear will be concentrated and turned into a vertical axis and produce a rotating updraft, which is the hallmark, the defining characteristic of a supercell thunderstorm. But in order to get that rotating updraft, you need to have the right profile of winds in the environment of the storm. And so those are the two basic ingredients to get rotating thunderstorms, supercells. You need strong instability, which is, that means warm, moist air underlying cooler air above it. And you need strong wind shear, strong vertical shear of the horizontal wind. There are other factors that come into that get a little bit more complicated, but I'll not get into that. But that gives you a rotating thunderstorm. That's still not enough, though, to get a tornado in a lot of cases. Because that rotation that you get tends to be in the middle part of the storm in the vertical. So like around 3 to 6 kilometers up in the storm is where from this mechanism, you will get the most rotation. In order to get a tornado, you need to somehow figure out how to get rotation down near the ground and much more concentrated. And that's where things get really complicated and where we're still learning the details of that. The gist of it is, though, that we think that a downdraft on the backside of the storm called the rear flank downdraft is important, and that it helps to transport some of that rotation from aloft, typically, and generate new horizontal rotation, which then gets concentrated near the ground and then pulled upward underneath the rotating updraft of the storm and producing a tornado. So there's a lot of stuff going on here, okay? And it's a very complicated dance between large-scale patterns and very small-scale processes in individual thunderstorms. So that's the basic answer, long answer to your question, but there's a lot more to it. I very, very much simplified as much as I can. So.
Thank you. Yeah.
Well, I don't think we'd understand if you went into the other.
Well, yeah, stop me if you have any questions about any of that point, because it takes a while to get to the kind of the conclusion there. You have to go through a lot of little steps. Yeah.
It sounds like there's an awful lot of physics involved with studying a storm.
Yep, it essentially is physics, right? Physics of fluids as applied to atmospheric flows on these different scales. Yep.
Oh, that is very cool. And I'm assuming so for like if we get into the high school level, those kids, some important classes if they want to be someone who's studying storms down the road to be like physics and math, the math classes.
Yes.
Or was that the two most important for them at this point?
Physics and math, lots of it. Yes, much as you can. Meteorology in general, not just for studying severe storms, but it just in general is very math intensive. So you need to learn, your linear algebra, your calculus, differential equations, partial differential equations. Those are all used extensively in meteorology. So that's important to lay the foundation for that as soon as you can. You're a high school student listening to this, and you're interested in this field, know ahead of time that this is a math intensive one. Don't be afraid. Just the more you can succeed in those classes, the better you'll position yourself. So there's that, and then of course the physics classes. Basic physics is very important to understand that. To lay the foundation for meteorology and atmospheric science. Also, increasingly, having an understanding of how to program and write and know your way around scripting languages and visualization and scientific computation is becoming increasingly important. We're trying to increase the exposure of students to that in our program here at Purdue in the undergraduate curriculum. But especially if you want to keep on going to a graduate or career or academic career, these are very important to know how to use the computational tools that are out there. So.
We're hearing that from more and more scientists across the fields, the importance of understanding some programming.
Right.
And so, wow. Well, thank you. Thank you for sharing about storms with us and formation. And thanks for your advice to the high school kids with the math, physics, and some programming.
Yeah, absolutely. If you can all do it, definitely go for it. Be proactive, be motivated. Yeah.
That's solid advice there.
Yes.
Well, thank you for your time. We appreciate you doing this.
Sure. Thank you for having me. It was great.
Thank you for listening to our podcast. Please hit the subscribe button so you'll continue to hear about new and exciting STEM-related work being done.
Tweet us questions, suggestions, and requests at Purdue SOS or email us at k12science@purdue.edu.
Until next time, be super, and remember, you are someone's hero. Boiler up!
Hammer down.